Welcome to T2 Day 28 of Calculus. Today we are going to make some boxes out of rectangular pieces of cardboard. So what's going on here is we have a rectangular piece of cardboard that's 24 by 18 inches. So we can just label that in there right now. So we know from here all the way to here it is 24 inches. And from here all the way to here it is 18 inches. Okay, let's just label that. Nice. And what's going on is we're cutting out corners of this cardboard and folding it up so that we make a box. And keep in mind we're kind of cutting out one side of each of these squares and then folding them back to make the box, just for reference. So the first question asks, what is the volume of the box formed when 1 inch square tabs are cut? So when we cut out a tab here where it's 1 and 1, well, we know the volume of a box is length times width times height. So if we cut out 1 by 1 on each of these corners here, what's the length and width and height going to be? Well, the height is going to be 1, but what is this going to be? Let's call this right here the width. If you cut out 1 and 1 on each side of this, this will be 16. And then what will this be right here, from here to here? If it's 1 on 1, 1 from each side of 24, that'll be 22. So h would be 1, length would be 22, and the width would be 16. So what does that mean the volume would be? That means the volume would be length 22 times width times 16 times 1. And I'm using dots for multiplication, which I really shouldn't do, but if you really want to stay on my good side, use parentheses like this. So I'm going to stay on my own good side and do that. So if I multiply that out, 22 times 16 times 1, you end up with 352 inches cubed. So what happens if you do the same thing but you cut out 2-inch square? You're going to do the same thing. You're using volume equals length times width. Ooh, and I want to stay on my own good side. So length times width times height. But in this case, let's use green this time. If we made them 2 by 2, instead of cutting out 1 from each, you'd be cutting out 2 from each side. So the height becomes 2. The height becomes 2, but the length also changes. Instead of cutting out 1 from each side, you're cutting out 2 from each side, so it's going to be 20. And then the width will go, instead of 16, it'll go down to 14. So in this case, the volume for this one will be length, let's keep it in the same order, 20 times 14 times 2. When you multiply that out, you end up with 560 inches cubed. Okay, that's nice. Let's keep going though. Let's keep going. Let's say we went all the way to 5 inches cut out for each square. So each square is going to be 5. So instead, let's say we went to 5. So each of these, well, let's use black this time. Let's say it's 5 and 5 and 5 and 5 all the way around. All these are 5 now. The height is now 5 because that's the height here that's getting folded up. So it's the same volume function, but h is going to be 5. What's the length going to be? 5 is going to be cut out of each side of 24, so the length would therefore be 14, and the width, you cut out 5 from each side of 18, it's going to be 8. So in this case, the volume is going to be length 14 times width is 8 times the height of 5. So what do you end up here? You end up with 560 inches cubed again, which is really interesting. So the volume of the box can change if you cut out different amounts from the corner to fold and create this box. The big question though is, if we wanted to maximize the volume of that box, what should the dimensions of the corners be that we're cutting out? Now it's rising and then something happens between here and here, so maybe it's between 2 and 5, or maybe it's beyond 5, who knows? But let's use calculus to find this. We're going to call, the important thing is call the side of the square x. We're going to call the side of the square x. So what's going on here is we have our sheet of cardboard, and here's the base right here, and the corners we're cutting out here, the corners we're cutting out will have side lengths x, 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 all these x's right here. This stays, the length, the overall length here of the piece that's starting out stays at 24, and the overall height here stays at 18. So again, we're doing volume equals length times width times height. And again, if you really want to stay on my good side, length times width times height, like that. So the height is x, as we kind of logicked out over here. The height is going to be right here. When you fold that up, that's the height. Well, the width is going to be 18 minus 2x because there's x's on both sides of that 18, and the length is going to be 24 minus 2x because there's x's on both sides being cut out from the 24. So now we know that the volume in terms of x is going to be length, 24 minus 2x length, times width, 18 minus 2x times the height of x. We now have volume just in terms of x. So we've expressed the dimensions of the box in terms of x, and then we found a formula for the volume. So we now want to maximize the volume. We want the greatest possible volume. So we need to take the derivative and set it equal to 0, a process we've done many times. But before we do that, let's multiply this out. I don't want to use the product rule twice on this. Let's multiply this out. So if you multiply this out carefully, first thing I did was I multiplied the x into this one. You can do it in any order you want. This is just what I'm going to do. And now I'm going to continue the multiplication. So I continued the multiplication and cleaned it up in one step. You can verify this yourself, but if you multiply that out, you should get 4x cubed minus 84x squared plus 432x. Now we take the derivative. It's just a polynomial, so we end up with 12x squared minus 168x plus 432. And as we've done many times before, we set this equal to 0, and then we solve for x. What's nice here is that each of these terms is divisible by 12, so you can just divide everything by 12. So end up with 0 is equal to x squared minus 14x plus 36. And now you're setting it equal to 0 and you want to solve, so you really hope that this is nicely factorable. If you test the discriminant, the b squared minus 4ac, it turns out it's not the best. It's not a perfect square. I'm being judgmental of numbers here. But let's try it here. B squared minus 4ac. If you do this out, it's negative 14 squared minus 4 times 1 times 36. You end up with 52, and that's not a perfect square. So that tells us that x is going to be equal to negative b, so negative 14 plus or minus the square root of 52 all over 2 times a, so it's just 2. You get two answers out of that. You get 3.394, and you also get 10.606. Now these are measurements of x. These are measurements of x. Now you should take a look and spot check these. Could x be 3.394? Yeah, it can. But what about 10.606? Can x right here be 10.606? It actually can't, because if it was 10.606, you would cut out more than you have. You only have 18 there. You cannot cut out 10.606 from both sides. So this is not a potential answer. But now what you need to do is you need to see that this generates a maximum with a sign diagram. So you have the 3.394 here, and that's an x value, and then you have v prime of x. And when you do the two sides of this, you have to the left of it and you have to the right of it. Pick numbers that are relatively close. I mean, what's the biggest x can be? You know the biggest thing x can be and still have a box. X has to be smaller than 9 because it can't, if it is 9, then you wouldn't have a width. So it has to be smaller than 9, and it has to be greater than 0 or you wouldn't have a height. So the smallest value, hard cap, down there is 0, and hard one up here is 9. So you want to pick numbers between the two, between 0 and 3.394, and between 3.394 and 9. And when you do this out, you do find out that the derivative is positive here, and it's negative here. So that means it's rising and falling, so this is a max. So we now know the max volume when x is equal to 3.394. But we need to go back and see if we're answering the questions. What size square tab? Oh, we do have the size of the square tab. We do have that. If you wanted to actually find the volume, if you wanted to find the actual max volume, you would then plug in x equals 3.394 into there. As far as I'm getting, you get the volume, not x. You end up with, so v of 3.394. As far as I can tell, you end up with 654.977. So that's actually bigger than what we got right here. Oh, dang it. Did I type it in wrong? Let's check it again. And yes, because I can actually read things, these numbers are smaller than this one. This is definitely bigger right there. I was reading it as 554. So we just showed that you maximize the volume of this box with an x value of 3.394, and it would generate a maximum volume of 654.977.